Certainly people have been thinking about outlier loci for a long time, including Fred and I back in 2000 when we were looking at Alaska Sockeye salmon populations. And at this time in 2000, there was this big switch over where you weren't just doing allozymes, but you had other kinds of DNA markers. You had microsatellites, you also had mitochondrial DNA. And so what we were trying to do is do a comparison and basically looking at the importance of different markers. So the take-home message is most of the markers were neutral, but there was this one here, SAH, that on any analysis stuck way out. And so we ended, in fact, I just looked at that paper last night, and we ended up saying, well, this is an exceptional locus, and we think it's under natural selection, period. That was about the extent of what we can say. So that's where I see big change is now we can start going in, we find these outlier markers, we start thinking about, okay, what are the genes, and what is it linked to, and where is it located in the genome. So there it is. Just a little bit of an outline of my talk. I'm going to talk about detection methods, how we use them in natural populations, then go back into one of our favorite salmon, Sockeye salmon, for an example. And then, if time permits and people are interested, we can do just a little demo on BayeScan. Okay, so we're going to start in terms of approaches to detect local adaptation. Basically, we sort of have these statistical approaches, and they fall into a couple of categories, be it differentiation based on FST, called the F methods, or correlation with environmental data. This obviously gets into landscape analysis and landscape genomics. So the two fields have really merged. But as Fred mentioned last night, and I had this slide in here before Fred even mentioned it, but as Fred mentioned last night, outlier analyses are not new, and they actually, Lewontin wrote this paper in 1973, and basically looked at the variance associated with FST across different markers, figuring the one that had the largest FST was the potentially under selection, and came up with if there is significant heterogeneity between loci and their apparent inbreeding coefficients, this heterogeneity may be taken as evidence for selection. So very, very simple, but that's what all these approaches, all these genome scan approaches are based on. But it didn't take other people long, Ney and Maruyama in 1975, to basically say, hey, no, that's not really right, because we have this problem of correlation across populations, and then that invalidated the estimation of the variance of FST, leading to a high rate of false positives. So here we are, 1975, we're also dealing with this false positive issue, as we will today. But then one of the biggest changes came in this paper in 1996, and it's the Beaumont and Nichols method. And what they did was come up with some null distributions, stochastic simulations to provide null distributions. And this was implemented in a program called FDIST, which was just pretty cumbersome. And so Tiago there wrote a very cool Java program called Locitan to implement the FDIST approach and Beaumont Nichols. And he was just telling me people are using that all the time. And the reason people are using that all the time is what Gordon talked about. It's a first pass to look at what are the outlier markers. And then in 2009, Sockeye and colleagues worked on a hierarchical approach, and probably many of you are familiar with this. This one is in Harlequin 3.5. And by the way, I'm going to show a lot of these papers. Don't worry about writing them down. I'll send everybody a file with all these papers that I'm citing, because it's probably about 20 or 30 minutes to talk about on the site. So don't worry about trying to get them all. Okay, and then BayeScan 2008 incorporated a Bayesian framework with FST as a model parameter, and Probably many of you are familiar with this, and those of you that aren't, that want to hang in there, and I will go through just a demo on BayeScan. But what it does is, it's looking at a Bayesian framework, it computes posterior probabilities of two models. One is the neutral model, and then one is a locus-specific model, and it compares these models. And it was kind of interesting. I hadn't thought of this as a classic approach, but then I heard Laura's talk a couple of weeks ago, and she goes, oh yeah, we did this as a classic approach. So I think, actually, I totally agree with her. This is the classic approach along with loci, and it's a very quick first pass, allowing you to see where your outliers are. You may have some false positives, but it's nice to start. And this is what a lot of people were doing, is looking at the overlap of methods. This is a paper that came out in 2012 by Marcosello. We have, I think we had a couple of his students, those guys here. And what they did is they were looking essentially for markers that might be particularly useful in population identification, in fisheries management, stock identification, and they did this kind of typical for the time, loci and the overlap with BayeScan, and then this other program, and probably many of you have seen these Venn diagrams. And that actually, ultimately, they came up with a very effective set of markers through this approach that, yeah, they're outliers, but they're very informative for splitting out particular populations. Okay, so that's kind of what I wanted to talk about, at least in terms of the classic approaches of the differentiation. Then we have the ones that start incorporating correlations with environmental data. And if you wanted to say if there was a classic one here, it would probably be BayeScan, which is COOP, and I think it came out 2010, and it also is a Bayesian method, and the null, it has a null model, and then it compares it to an environmental model at each SNP. So the environmental model is looking at where an environmental variable has a linear effect on the transform frequency. So it's through, again, this Bayesian framework incorporating environmental variables. So this is a paper that came out in 2012 by Morten Limborg, who was a postdoc in our laboratory. He did this for his PhD, and he was looking at Atlantic herring. And he did the typical BayeScan, and he actually found, if you aren't familiar with the plots that come out of BayeScan, he found quite a number of outliers over here stacked up with a very, very high probability of being under selection. And then he incorporated BayeScan, and in BayeScan he would have environmental variables. I think he had several, but the ones that were significant were temperature and salinity, and he was able to show that they were significantly associated, that they were form markers significantly associated with salinity and temperature, and then looking at the overlap. So this is one of the first papers that came out and used both types, the FST differentiation and environmental and correlation approach. Okay, so I told you all that. Now the question is, okay, you've got these multiple paths. Which ones do you use? What are the different? You're smiling there because I'm sure that Laura's just been through this.
All of them.
Yeah, I'm having it. I'm sure other people have too. Any of you that have gone down and have some data sets that are fairly well along have been through these analyses or through this process. So what do we do? Well, there are a lot of pretty smart people that like to evaluate methods, and this is what they do, is they spend a lot of time, and this is Stephanie Demitta. This paper is it's a good paper. It's a great starting place for people to use. It's not really too dense, and you get the big picture pretty quickly. And what they did is they looked at 8 different methods for their effectiveness, and they did something interesting though. Of course, it wasn't just straight, they were looking at sampling strategies. So now we got to think about, okay, how does sampling strategy and you have these different methods and how do they interact and which ones are more sensitive to particular sampling strategies. And so they used here, where they used many populations and few populations and many individuals. Again, other people have talked about it. You have a certain amount of sequencing dollars. How do you want to spread them out? You want lots of individuals, a few populations. So that's certainly something to look at, and obviously they looked at it. And then they had different demographic models. And so they had the island model and the stepping stone model and the hierarchical model. So they had this matrix of different sampling strategies along with different demographic models. And they looked for false positives with these 8 methods. And the first thing that they found, and actually this was 2013, but subsequent papers have also found this, is that there's more power to detect selection. For environmental methods, have more power to detect selection than differentiation methods, but they can have high false positives. So now you kind of have a conundrum. Okay, it's more powerful with these environmental methods, but I'm going to have to deal with the same problem with positives. They found it accommodates complex population histories like isolation distance and has a lower false positive. So the take home from this, and it's a little bit hard to see, but one of them, this FG, you probably can't see it right here, but this one performed really well. This is BayeScan. And you'll see a number of papers will say, well, we looked at BayeScan compared to some of these others because it has a lower rate of false positive. Demita et al. 2015. And that's based on this. And they also found, and this I would just kind of take as a grain of salt because it was really based on their particular simulations, better to sample few individuals in many populations. So I wouldn't hold on to that. Okay, so those are what we call the classic, but that was, as of 2013, we're in 2015, so there's been a whole lot that's come out in these 2 years. It's getting a little harder to keep track of these methods, actually. And the methods have started to merge a little bit between the differentiation methods and the environmental association. So what we have now is this paper called, I don't even know how we say it, it's like BayeScan Enviro something. I don't know, call it whatever you want. It's essentially a BayeScan that has included an environmental variable. So they include environmental differentiation, but it's effectively a genome scan method that has environmental variation in it. So we're starting to see sort of the merging, as I said, the merging of these 2 different ways of going about it. And instead of having the 2 models, the neutral and the divergent selection models, and the comparison that one would see in BayeScan, it's gone to these 3 models. So it has the 2 that are in BayeScan, and then it's comparing another model that has the environmental differentiation. So I haven't ever used this. I don't know if Laura has used this or not. How did it perform?
Perform well, but as the same as BayeScan. I mean, it detects just only sites that have high differentiation. So it's kind of, there's a lot of overlap between like the SNPs that you detect with BayeScan and the one that you have. I mean, I just have one parameter, which was temperature, but it's important to just think that this method cannot detect subtle shift of high frequencies that could happen when you have like a gradient, for instance. The selection could be like slow and not like very high or showing high divisions. So it's great to use this method. There are other methods that you can also detect subtle shift in frequencies that could be maybe more appropriate for you depending on the parameters that you have.
I'm not sure how many methods you used, but it was probably above 5 or more that we used to.
Yeah,
I'm going to show a couple of them.
Yeah, we use LFMM too.
Okay.
Yeah, which is a method developed at the same, not the same lab, but both labs are working on Grenoble in France. And that was great labs too, but like they developed at the same time BayeScan and LFMM. LFMM, it works in a different way. It detects structural shifting higher frequencies. And what's great with LFMM is when you have genome or like reference, you can do Manhattan plot and have the correlation like random forest. And if you heard about these techniques, like you test for correlation between the markers, and so you can detect structural shifting higher frequencies with correlation between the markers, which is kind of nice because we all know that the problem now is more like false negatives and false positives, right? Because we have a lot of synapse sections that we don't detect with this kind of techniques. So we can detect with other, like LFMM and stuff.
This is the one that this one that you were talking about that I just going to talk about here. Another one of the emerging environmental methods, and this one is latent factor mixed models, so LFMM. It's based on variant principal component analysis, and it combines population genetics, ecological modeling, and statistical learning techniques, and obviously it has some nice qualities when you're looking at this. So what is effectively how it works is that it has these unobserved latent factors, and you evaluate how many of those factors provide you the best results. And these latent factors are what represent demographic history, unknown environmental pressures, or from isolation by distance. And it's very similar to structure in terms of you will need to go through and look at how many of these factors provide the best result. And there was a paper that came out in July of 2015, Molecular Ecology, and this one was on nuthatches, and they were looking at kind of a landscape genomic approach, and they used BayeScan too. That was the first one. But this table that I'm going to show was basically come from Bayen and the latent factor LFMM. And they had a couple of variables they found that were important. Was I think this TWM is temperature, and this is some precipitation. And they looked at, I think they looked at 9 factors, and they found significance in latent factor 1, latent factor 9, and then in Bayen. The next step that they did, and this is something, again, a big change from population genetics, now we're in population genomics. They went and this is in nuthatches. I'm not a bird expert. I don't know how close nuthatches are to zebrafinches, but they used the zebrafinch genome, and they were able to identify what chromosomes they were on, have these particular loci, and then were able to class them. So this is, I think, what we're going to be seeing more of. More of using these resources, either developing yourself, tapping into these genomes that are available, and Paul talked about a lot of them, and doing annotations. And you wouldn't, as no surprise, they found some isolation environment. Okay, so do I have any sort of take home? It's a lot, maybe not quite as bad as it might seem, because there have been quite a few more comparative studies that have come out, and this one in 2014, linear regression, BayeScan, LFMM, so latent factor. This is another interesting one, and this one I just got, I think it was just early online on Friday, and that's in molecular ecology. And this one looks at a whole host of methods with environmental association. So if you haven't seen that one, take a look at it. It's really online in molecular ecology. And then keep in mind that all these methods vary with sensitivity to population structure and history. You still have to know your organism, know your question, know your sampling design. And the power that you have may depend on actually the genomic architecture, which you don't have much control of. But for example, you might have small allele frequencies at many loci, you might alternatively have few very large loci. So the different methods are going to be sensitive to this. And so if you explore multiple methods and types of analyses, there's a couple of different ways to do it. One, and I think every paper that I have shown has really done it in parallel. So they look at LFMM, and they look at BayeScan, and they look at Bayen, pretty much in parallel. There's another approach, and that is sequential, and I wasn't able to find a paper that actually did it, but effectively the idea here is that you have the output from one, and that becomes the input to the next one. So there are other ways to think of it, other than just kind of going down and going parallel. And one other thing that I was able, to glean when you look at some of this is from the 2015 paper, is think about how some of you it's maybe too late, others of you haven't designed your sample yet. Think hard about sampling design because sampling locations chosen in pairs that are geographically close but selectively diverged can increase power, so that is something that you can control on. And the power from these paired strategies may exceed the power from just straight adding more samples and increasing sample size. And that's because within these pairs, the neutral loci will not be greatly differentiated, but the selected loci will. And it's really the difference between these neutral loci and these selected loci that gives you the power to detect. So if you have a lot of differentiation of neutral loci, it's going to be tough to find these selected loci. And I'm going to show that a little bit more in one of the examples from Sockeye. Okay, so we got through the statistical, just really quick on replication, which is actually consistent with what I was just talking about, and the way people, and this one is actually an old paper by Ian Bradbury, old, I think it was 2010, but this was looking at two sides of the Atlantic, and this is the parallel approach, so parallel adaptive evolution of Atlantic cod on both sides of the Atlantic, and they showed that for temperature-associated climes, they had the similar outliers are in red here. These are, of course, BayeScan plots. So they have Eastern Atlantic and then Western Atlantic. Okay, so the next thing really kind of shifts gears. I want to talk about candidate genes and functional categories. And our labs worked on Sockeye salmon. It's been well known that MHC, the major histocompatibility locus, is quite variable and is an outlier in many Sockeye populations, particularly in British Columbia. So we looked in Alaska, we had graduate students, and Daniel, this is his paper, he was postdoc with us a few years ago, and found, okay, these were SNP loci, and found these two MHC. So again, from the candidate approach, one of our current, actually he just graduated, he received his PhD last year. I think he just received his PhD last week. I think it's final postdoc in the lab. But one of the projects he did was build on some of our MHC work of Daniel and Lonnie McLaughlin and a couple of other people, and just take it a little bit further. Now, this, I'm going to talk a lot about the Sockeye salmon and ecotypes up in Alaska in Bristol Bay, and he did his work there. But this is really, here's the take home on the MHC. And if you look at the mutual SNPs and FST, 0.01, MHC 0.27. So that's the candidate approach. And one of the nice things about this system, that, which I'm going to talk about, is neutral divergence is so low. Right here, the mutual SNPs is very low. So that when we do see these potentially selected markers, we have enough power to detect them. And this is just a little bit of his data. This paper was published last year, and he had 3 different ecotypes. The first was the beach, and what he did, rather than just what had been done by Daniel and previous, is he'd actually gone in and he'd sequenced, I think it's 190 base pairs, so he had done Sanger sequencing. This is He did Sanger sequencing, that was the cheapest way, and got, I believe it was 16 haplotypes. So what you can see here are, these are 2 ecotypes from the beach, not a lot of diversity, and we interpreted that. There has really been a directional selection. Then he started looking at river populations and stream populations and found quite a bit more diversity associated with these ecotypes. And it likely has to do with pathogen loads and temperatures that differ between the ecotypes in each streams. That's a working hypothesis. Yeah. But again, if you were to look at these mutually, really wouldn't see much. Okay, then a really big area, and we've already seen it in a number of studies, is the mapping of outliers. And I'd like just to start with this idea that you do whatever you want to do, whatever BayeScan, Bayesian, or something, and you end up with all these anonymous adaptive loci. These are FST. This is somehow a list, just stacking up your 10,000 loci for whatever. And that's cool. It's kind of neat. You've got some outliers. But you're really in the dark. And if you start looking at genomic position, and all of a sudden you can see there's certain areas of the genome that are differentiated. And Fred's not here, but this is what I think is another big difference between population genetics and population genomics. Now, we aren't looking just across the genome. We're looking, and Gordon talked about this too, we're looking at subsets of markers. We're looking at particular regions. We're looking at islands across the genome. That's a really big difference, and not, nobody even thought of this. Even 5 years ago, we really didn't have the ability to do this. So now we do. If any of you recognize this, this came from a study published in 2013 by Jacob Hansen, and it was looking at differences in cod between the migratory type and stationary type, and these are his different linkage groups, 1, 2, and 12, that he found these really interesting islands of oranges. Okay, so here we are, and we can start thinking about when you go in your study. Can you do differentiation tests? Do you have some correlation in the environment? Can you do replication? Do you have some candidate genes, or can you align, and can you annotate, and can you map your outliers? And I didn't use Martin's slide, he's our postdoc, but he has this really cute slide that has these smiling faces on it. So instead of checks, you've got like 1 here, and then if you get down to here, you have 2, 3, 4, and 5 here. I couldn't do it. But he has a slide that shows, okay, so really what we're trying to do is bring more and more evidence to our hypotheses and what we're seeing and verifying the genes. Okay, I'm going to go, I have a drink of water, but then I'm going to go into this Sockeye salmon study that we have been. We've been working on Sockeye salmon for a long time. I started studying for Fred. And kind of show you where we're at.